A warm welcome to one and all gathered here. The Department of Statistics, DRBCC Hindu College, proudly presents Statistic Association Inauguration with the presence of renowned Chief Guest, Dr. G. Gopal, Professor and Head of the Department of Statistics, retired University of Madras, and Honorable Principal, faculty members, our young statisticians. Prayer is a tool to refine our thoughts, to add on divine vibration to the event. Let's have a prayer. I request the gathering to stand for the prayer. Tipa Priya, Head of the Department of the Statistics, to present the welcome address. Good afternoon, one and all present here. With the blessings of our founder parents, I welcome you all for the inauguration of Statistics Association. We have amidst renowned Professor, Honorable Chief Dr. G. Gopal sir, who is known as man of references. When you speak about or when you talk about a topic, sir will give enormous references. He has guided many PhDs and also MPhil scholars, and he has more than our age experience. So such a chief guest is a miss, and I hope he would provide you a keynote for the probability. And I welcome our Honorable Principal, Dr. G. Kalvikarasi ma'am, and also I welcome our Director, and I welcome all my colleagues, and also I welcome the freshers. This year, the syllabus enriched, and also the association has a key headed with lot of activities. And for example, the seniors of your department, Balaji, Sai Shruti, Venkeshwar, along with some of the second year and third year, have planned to open a LinkedIn page where you will be posted with lot of academic writing as well as memes and other posts about statistics, which would balance all these slow learners and the advanced learners. Maybe it would be an opener for all the creative writers. So like that, every year this association have done its new thing. Likewise, this year it has planned to open a LinkedIn page which is known as professional page. And I welcome all my dear students and also my friend colleagues for this inaugural ceremony. Thank you. Thank you, ma'am. It's of course a proud moment to shoulder the responsibilities. Starting ceremony, I request President Ms. Apita and Vice President Mr. Prashant. Apita has gone for internship, so I request our principal to honor the student with his badge. Thank you, ma'am. I request our honorable principal to share few words to the students.
Respected head of the department. No? Hello. Hello. Respected head of the department, Dr. Deepak Priya, the learned colleagues of the department and the freshers. My greetings to you all. I'm very glad to join you all for the inaugural function of the Statistics Association. First, I congratulate all the freshers for having taken up a very wonderful course which fetches lot of career opportunities. So this is where I think that you are all very intelligent for having chosen the course. And as you all know that every minute the students pass out after 3 years, immediately many of them get even government appointments in almost in various departments, not only in teaching, but also in several government organizations, research centers, and also in other private organizations. So this is a very wonderful course and I congratulate every one of you for having chosen this course. Next, I understand that Dr. G. Gopal, our chief guest of today's Tech Talk. This is one of the departments which also is very tech savvy. And the institution takes a lot of help from your department in analyzing about the status of the college or whether we go in for accreditation and wherever help is needed, we make much use of the department faculty members. At this juncture, I also offer my thanks and felicitation to the department colleagues, the faculty members, for having been so contributory to the development of the institution. So our chief guest, Dr. G. Gopal, is a retired professor and head Department of Statistics from the University of Madras. Also understand that he is also the postdoctoral fellow at Florida State University. And looking at this illustrious profile, our student must be really lucky enough that Dr. Gopal could spare his valuable time and also after several years of his retirement that he is so very enthusiastic to speak with the students and give a lot of input. I take this opportunity to thank Dr. Gopal for having accepted our request and to deliver a very useful lecture to you all. I think you have made a very good beginning with a very scholarly person as the resource person for today's inaugural function of the Statistics Association. So I convey my appreciation to the faculty members and also the freshers because you have come with a dream and you all must achieve that. I pray God Almighty and Founder Couple to shower their blessings so that every one of you will have a more prosperous career. Thank you.
Thank you, ma'am, for your valuable speech. I request Dr. J. Rajesh to introduce our chief guest.
Good afternoon, one and all gathered here. So I'm happy to introduce today's chief guest, Dr. G. Gopal, retired professor in Department of Statistics, University of Madras. He has 34 years in teaching and research experience. He has studied master level from prestigious Department of Presidency College, Chennai. So he also academic support from Dr. J. Ranganathan, so he has obtained MPhil and PhD degree under the guidance of Professor K.N. Second Raman and Professor K. Suresh Chandra. He has completed MPhil and PhD degree under the guidance. Okay. Next, he has postdoctoral fellow in Florida State University during the 1988 and 89 under the Government of India fellow. His area of interest, reliability and survival analysis. He has guided 10 PhD scholars and 15 MPhil scholars. He has to credit 30 research publications in reputed journals. He has delivered several invited talks, workshops, seminars, and conferences. Sir has integrated actuarial science at the University of Madras at master level in University of Madras. He has a recognition of his service to the subject. The Institute of Actuaries of India awarded honorary fellow of the Institute Actuarial of India in 2001. He has also served expert of various universities across the country and different organizations such as UGC, UPSC, SSC, etc. He has traveled academic purpose of several countries like USA, France, and Japan, etc. Once again, I welcome Sir attend the gathering.
Thank you, sir. I request our chief guest to share his words of wisdom.
Be cheerful. I find you are very serious. Statistics department is not always easy. Mercial. All of us scared. You have a wonderful department. They are very helpful and definitely I know that you will have a very brilliant career. Right? All the best.
Hello? Hello? Shall I continue? Hello? Do you hear me? Hello? Thank you. Hello? Shall I continue with the talk? Okay. I am thankful to the management, faculty and students for having invited me to deliver a talk on the occasion of the inauguration of the Statistics Students Association. This college is not new to me. In fact, I will never forget the financial support extended by the management when I organized an international conference at the University of Madras way back in 2000 in honor of two distinguished professors of Madras University. I am also thankful for the support of the former Professor Chinnappa Chetty and Professor Ramakrishnan for their support at the time. My sincere thanks to the management for permitting the college to offer a degree course in statistics. In fact, I only framed the syllabus as the then chairman of the Board of Studies in Statistics of the University of Madras for the BSc Statistics course, which was offered only in DRBCCC college under non-autonomous pattern. I am thankful for the support extended by Dr. Kalpana Bai and Dr. Pari for that purpose at the time. And few days back, Dr. Deepa Priya called me to deliver a talk for the students or for the benefit of the students of statistics at the college. In fact, I am thankful for the principal, Dr. Kalvi Karasi and Director N. Rajendra Naidu for their support. And I am also thankful to the other staff members, Dr. B. Vijay, coordinators A. Gopinath and U. Parthiban for their support for organizing this seminar and having invited me to deliver a talk for the benefit of the students. Thank you. Now let me start the lecture. The topic given to me is dealing with the events probability. Now, broadly speaking, statistics rests on four pillars: probability theory for inductive logic, statistical inference, another main branch of statistics for meaningful interpretation of information in the given data, design of experiments, and sampling theory. They are methods for collection of required data. It is the strength of these four pillars that has made statistics as an inevitable tool for the data analytics and data science. Next slide. Next slide, please. Next slide, please. Next slide. Go to the next slide, please. Yeah. Therefore, brief history and all you have skipped now. For understanding statistics, you need some basic mathematics like complete knowledge of set theory, the knowledge of function. The function concepts are very, very important, and the knowledge of elementary calculus are essential for understanding the probability theory. Next slide. Next slide, please. Interpretation. How do you interpret probability? Before we define probability, let us ask what information does it give? How do we interpret in practical situations? It is a relative measure of degree of certainty associated with the occurrence of an event in a single trial of an experiment. For instance, if probability of any event A is 0.5 and probability of B is equal to 0.6, then B is more likely to happen in a single trial than A. Similarly, probability of rain today, 0.5, does not mean it rains 12 hours in a day and 12 hours it doesn't have any rain. And does it rain in the remaining time? This is what it is used in testing of significance. If P of A is less than 0.05, we usually conclude that A is not likely to occur in a single trial experiment. This is the basis for our conclusions in testing of hypothesis. Go to some slide. Please advance the slide. The person who is operating on the other end, kindly move the slide. The slide doesn't move. Hello? Hello? I don't know what to do. Everyone is hearing and everyone is listening, but the slide doesn't move. The slide. Hello? 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 Please move the slide. You have gone fast. Axiomatic definition. We have escaped a lot of slides. See, there are three approaches for probability. Probability, when you start, you will have to define what is an experiment, whether it is random experiment or deterministic experiment. In probability, we use random experiment. Then you collect all possible outcomes. Then you form a set. That set is called the sample space. And any subset of the sample space is called event. And the probability of any event is given by three definitions. One of them is classical definition, where there the number of, suppose probability of event A is needed, P of A is equal to probability of the number of points in A divided by number of points in the sample space. That will be a number lying between 0 and 1, that is probability. And this definition suffers from some drawbacks, which means when you move the sample space from finite to infinite, it doesn't work. And similarly, you are trying to define probability through another term equally likely, which is again meaning probability. Therefore, these difficulties face another definition, which is the frequency approach. In the frequency approach, what we do is you find to repeat the experiment n times and observe the number of favorable outcomes in that experiment. Take the ratio m by n. Allow this limit n tending to infinity. Therefore, in the long run, you repeat the trial and whatever comes, that is your probability. Here also we have some problem which is limiting probability. For example, we say tossing a coin, probability of head is half. Suppose you throw 6 coins. You cannot expect 3 coins head, another 3 coins tail. 2 coins may be head, 4 coins may be tail. But if you have more number of coins, maybe 1000 coins, if you do that, then if you compute the ratio, number of heads divided by total number of players, that will approach to half. That is a limiting approach to probability theory. The another definition, this is axiomatic approach to probability, that is given by Kolmogorov. A.N. Kolmogorov, Russian mathematician, he gave that probability. That sounds very good. Through that only the probability has been developed, the modern probability. Three axioms. Axiom 1, axiom 2, event is bigger than or equal to 0. Probability of union of AI is equal to sum of probability of AI. The events are disjoint. That is what this means. AI cross AJ is equal to pi null set. And the probability of the full set, the sample space is 1. Based on these three axioms, the entire probability theory is developed. These axioms are due to A.N. Kolmogorov, the Russian mathematician, probabilist. This approach paved the way for the development of modern probability theory. If A is a subset of B, then probability of A is less than or equal to probability of B, and probability of pi is equal to 0, and probability of A complement is equal to 1 minus P of A. Complement here is something which makes full. A with A complement is the master set. That is what complement means, C-O-M-P-L-E-M-E-N-T. Next slide, please. Next slide, please. Next slide, please. The proof for all these consequences are not given, and it can be easily proved. The next slide, please. Hello? Next slide, please. Next slide. Next slide, please. What to do? gone to Bayes' theorem. You have gone to Bayes' theorem. The Bayes' theorem, independent events and all gone. The conditional probability example of, see an example of total probability and Bayes' theorem. Here on contains one white ball and two balls. On B contains two white and one black ball. On C contains three white and three black balls. A die is rolled. See here we are going to choose the on. If 1, 2, 3 turns out, on A is selected. If 4 turns out, B is selected. And 5 or 6 turns out, C is selected. Therefore, for selecting the on, we use these probabilities. Probability of selecting on A is 2 by 6. Probability of selecting on B is 1 by 6. Probability of selecting on C is 2 by 6. Now, a ball is selected from the on, selected, and it turns out to be white. What is the probability it comes from on A? This is inverse probability. Now, see, probability of A is, next slide. Right. Probability of A is 3 by 6. B is 1 by 6. Probability of C is equal to 2 by 6. The total probability of white, what we want is probability of selecting white, which is equal to probability of W intersection A plus probability of W intersection B plus probability of W intersection C. How we get it? Probability of omega intersection W, but omega is A union B union C, both of them disjoint. By De Morgan's law, you can get that equation. Again, by definition of conditional probability, you get the next equation. And the probability of the on is A. What is the probability of selecting white? That is given by 1 by 3 into 3 by 6. Like that, it goes from for all these ons. That is called the total probability. Now, a ball is selected. A ball is selected and it turns out to be white. What is the probability that it comes from on A? That is given by probability of A intersection W by probability of W. By definition of conditional probability, you can write this equation in the numerator, and this denominator is the total probability. When you simplify this, that is 3 by 8. Therefore, if it is A, the ball selected is W, the probability that it comes from A is 3 by 8. Similarly, you can compute for B that the ball it comes from B, some value will be there. Similarly, for C, another value will be there. But when you add all of them, it will be equal to 1. That is the Bayes' theorem. But Bayes' theorem, even though this is a simple theorem, it finds a lot of application, now a lot of in statistics. And there is one inference called Bayesian inference that really rules the world now. It has lot many applications. A lot of people are using the Bayesian inference based on this Bayes' theorem. Bayes is a very powerful person. He published only 2 papers, and that too was published posthumously. Next slide. Move on to the next slide, madam. Right. This is very, very important, random variables. Random variables. See here, so far we have discussed how to compute the probability of events. Therefore, we conduct a random experiment, you find the event, computation of probability of events are there. Then what is the need for a random variable? The random variable comes naturally. Suppose 2 women are playing a dice game. The dice consists 1, 2, 3, 6, 1, 2, 3, 4, 5, and 6. Another die again 1, 2, 3, 4, 5, 6. Now they throw the die simultaneously. Die 1, 1 comes. Die 2, 2 comes. Therefore, the event here is 1, 2. But they don't say 1, 2. Immediately they say 3 has turned out, which means they are not interested only the outcome, but they are doing mathematics there. What this mathematics? They compute, they sum the outcomes. 1 plus 2, which is 3. Therefore, they define a function on the sample space to realign, which means they say immediately 3. Similarly, if 4 comes, they say 8. They add these two outcomes. In fact, without knowing that they are defining a function, just like that, without knowing that they are doing a function, they define a function on the sample space. Therefore, random variable is a function defined on the sample space to real line. Real line is minus infinity to plus infinity. Strictly speaking, x is a random variable. This is a sample point, omega to r, such that the inverse image of the type x less than or equal to x real, are the events in the space. This is called a measurability condition. Later, when I define this distribution function, we will be using these type of symbols for defining the distribution function. Though through x we can generate interested events, we may not be interested in all the subsets of the sample space. Through this x, we can identify those events which are interested to us and define probability for that event. And again, the name random variable, it is a function, it is not a variable, but people called over period of time random variable. But because already it has been using for a long time, they don't want to change that name. It is going as such. Therefore, it is a misnomer. It is not a random variable. It is a function defined on the sample space to the real line. A continuous function of a random variable is also a random variable. This continuous function, which you would have studied in your 12th class, and the inverse map of open set is an open, is also a random variable. These are all some concepts on the random variables. Once you define, therefore, finally, we can say the random variables generate events, and through that events, for those events, we can define probability for that event. Next slide, please. Next slide, please. Madam, move on. Yeah, distribution function of a random variable. The distribution function play a dominant role in probability theory. If you know the distribution function of the random variable, the entire history of that random variable can be studied. Therefore, the distribution function must be properly understood, and if that distribution function is not known, the statistical inference comes. Therefore, how do you define the distribution function? F of x, this is a real function, probability of x less than or equal to x. For defining the random variable, we used this x less than or equal to x. Unless this is an even, we cannot define probability. Therefore, in order to qualify to be a random variable, the function has to satisfy this condition: x less than or equal to x must be an event. On identifying this as an event, then probability can be defined. You assign that probability to the functional value of f of x. Recall the definition of random variable earlier. This function plays a key role in statistics and tells the probability statements about the random variable x. Here, see, a lot of things are going with the use of the distribution function. Without the knowledge of the distribution function, we cannot say anything about the random variable x. Suppose it's not coming. Yeah. See, you assume that a population has a characteristic x and it is a random variable. Therefore, to study about the population, we need to know about the distribution function to tell about the statistical probabilities like mean, variance, skewness, kurtosis. All these things can be studied through the knowledge of the distribution function. That is what we do in our statistical inference. What are the properties? The properties here are f of x, this is bigger than or equal to 0. This is non-decreasing. If x is bigger than y, then f of x must be bigger than or equal to y. And this is the limiting right continuity property. Limit as x, f of x plus s as h goes to 0 is equal to f of x, which is called the right continuity property. And this already is there. If it is left continuous, then it is continuous. But left continuous may be there or may not be there. But right continuity is always there if you define the distribution function like this. Similarly, limit as x tending to infinity f of x equal to 1 and limit as x tending to minus infinity f of x is equal to 0, and this property is called a normalizing property. This is right continuity, this is non-decreasing, this is non-negative. These are all the properties of the distribution function. If you take any mathematical function, if satisfies these conditions, then immediately we can say that this is the distribution function of a random variable. A random variable is behind, and it may not be easily visible, but it is there. Through that only we get this distribution function. Next slide. Next slide, madam. Yeah. Discrete random variable. The discrete random variable is a random variable which assumes only a finite or countable values. It doesn't assume uncountable values. The probability mass function Px of discrete random variable x is defined as probability of x equal to x. X is the value of the random variable, and it must be equal to 0. Otherwise, if it takes this value, x value, then the probability is assigned for that. Other values of x, the probability is 0, with the condition that p of x equal to bigger than or equal to 0, and when you add some probabilities, it must be equal to 1. The distribution function of a discrete random variable is f of x equal to, you'll have to sum the probabilities up to x, This r is a dummy variable. Sum over r less than or equal to x, probability of x equal to r. Clearly, f of x satisfies all the properties, and notice that probability of x equal to x is bigger than 0 for some x. If for all x it is equal to 0, then this will be a continuous random variable. At least for some x, this must be bigger than 0. Next slide. Continuous random variable. This is another important function. A random variable x is called continuous random variable if its distribution function f of x, as I told you, f of x is the cumulative function. As x advances, the probability also gets augmented. That is expressed as f of x equal to minus infinity to x, f of t dt, x real. Therefore, you are cumulating the probability up to x of the function f of t, where f of t is called the probability density function of x. That is, by definition, this f of t is bigger than or equal to 0 for all x, and minus infinity to plus infinity f of t is equal to 1. It is to be noted that f prime of x, the first derivative of f of x is equal to f of t, and this f of t is the probability density function. For continuous random variables, another definition for continuous random variable x is probability of x equal to 0 for all x. For every x, if the probability of x equal to x is equal to 0 for every x, then it is a continuous random variable. For a continuous random variable, you cannot find the probability at a particular point. The probability at a particular point will be always 0, because at the particular point, if you have the graph of f of x, You take a particular point, if you project it, it is a line, it is only a line. But for continuous random variable, probability is computed for a rectangle. It is only a line. For a line where is area? Area will be equal to 0. Therefore, one of the definitions for continuous random variables is probability of x equal to 0 for every x. For all x, it is probability is 0. Then such a random variable is called a continuous random variable. Or more precisely, the probability for x lying to between a and b is given by a to b f of x dx. This is what the continuous random variable says. This f of x is called the probability density function of the random variable x. Next slide, please. Chebyshev's inequality. It is a powerful inequality. That inequality says, suppose x is a random variable with mean mu and variance sigma square, then probability of mod x minus mu bigger than epsilon is always less than or equal to the variance of x by epsilon square. And this inequality is used to prove one of the important properties of an estimator, the consistency property. This is the definition. Using this inequality, we prove that for large n, the estimator converges to the parameter, the mean for large n. That property Next, bivariate random variables. Bivariate random variables. Suppose instead of one random variable, you have two random variables, x and y. One x denotes the height of an individual, y denotes the weight of the individual. It is a two-dimensional random variable. Then the joint distribution function of x and y is denoted by f of xy, which is equal to probability of x less than or equal to x, probability of and y less than or equal to y. This semicolon means intersection. This is that of all points omega such that x of omega is less than or equal to x, y of omega is less than or equal to y. Both x and y are real numbers. Increasing and right continuous with respect to each coordinate, as in the case of the previous one-dimensional case. This property, limit as x tending to infinity f of xy is equal to f of y, which means if you allow one of the coordinate to infinity, then this event corresponding to this event, that becomes a full space. And if you intersect by using this definition, if this is infinity, this event is the master set, intersect with this, the smaller event comes, that is f of y. Similarly for this, when you do this for x, you get f of y. When you do for y, you get f of x. Okay, you have moved to an example. Therefore, this last property is very, very important. The x1 less than x2, y1 less than y2, f of x2 y2 minus, okay. This property is a very interesting property. F of xy is equal to 0 for x is less than 0. If x is less than 0, it is 0. Similarly, y is less than 0, it is 0. When x plus y is less than 1, x plus y is less than 1 is below this line. Below this line, it is 0. Therefore, above this line, it takes value 1. Otherwise, it takes value 1. Therefore, such a function is given here. Now, this function satisfies all the conditions. Condition 1, 2, 3 above but not the condition number 4. If the condition number 4 is very crucial condition, without that condition it is not a distribution function of a bivariate random variable. What does this condition say? This condition says probability of x less than 1 bigger than 1 by 3 and the probability of y less than 1 bigger than 1 by 3, that is given by, see here, 1 1, this is x2 y2, this point minus 1 1 by 3, one of them, this is x is 1, y is 1 by 3, this is y is 1 by 3, x is 1, and f of 1 by 3 1 by 3. Therefore this condition has to be satisfied. If you see the graph from this function, f of 1 1 is here, this point is 1 0, this point is 0 1, 1 1 is somewhere here, this point is 1 1, this value here is 1, therefore that is 1 here, the 1 here, 1 3, 1 3, see here 1 is here, x is 1, y is 1 by 3 here. This is the point at which the value of the function lies. But here it is 1, therefore the minus 1. Coming to this 1 over 3, 1, see here, this point lies here. The y is 1 over 3, but x is 1. Therefore, x is 1, y is 1 over 3 here. This point is here. Therefore, the first three points are here and here and here, all of them above the line, which means 1 minus 1 minus 1, 1 by 3, 1 by 3. 1 by 3, 1 by 3 is corresponding to this point here, this point somewhere here. That value is 0. Therefore, if you have a function like this, at 3 points 1 1 1 and this point it is 0, you have this condition 1 minus 1 minus 1 plus 0, which is equal to minus 1, which is not bigger than 0. It is a negative quantity. Therefore, even though this function satisfies all the conditions, namely non-negative, non-decreasing and normalizing condition, it has to satisfy this condition also. And if it satisfies this condition, then only you can say this is a distribution function. Otherwise, it is not a distribution function. Okay, next slide, please. Next slide, please. Oh, okay, you have changed. Oh, independence you have escaped. Expectation of a random variable. So now you have two random variables, discrete and continuous. If x is a discrete random variable having probability mass function p of x, then the expected value of x is defined as expectation of x, which is equal to x into p of x. Similarly, if x is a continuous random variable, then expectation of x is x into f of x. Here we define this integral in a simple way, but expectation is an integral. This is an integral. When you go for higher studies, this will also be treated as an integral. This will be, if you are doing MSc, master's degree in statistics, you will learn that this also can be treated as an integral. Therefore, expectation is a general integral called measure integral. We have integral in mathematics also. When you look at mathematics, the integral will be, the expectation will be in integral, and we have integral in mathematics also. There is a small difference in the conditions we impose for these integrals in statistics and mathematics. See, the mathematicians will not accept as such this integral. They will say the expectation exists, it must be finite for this integral, then only you can make use of this integral. And for them the integral to exist. Otherwise, they will not accept this as an integral. You will be exposed to such refinements as you progress further, namely when you are doing your master's in statistics, you will understand more on this expectation of a random variable. Okay, next slide. Now, law of the unconscious statistician. You can think where this statistician will lose their consciousness. In fact, the statisticians are more conscious people. But there is a rule which says that law of unconscious statistician, what this says is, if X is a random variable, discrete random variable, having probability mass function P of X, then the expected value of G of X, namely if you say G of X equal to X square, say, is defined as expectation of G of X, which is X square, then you make use of this definition sum X square into P of X. But in fact, if X is a random variable, you'll have to find out the distribution of G of X or the distribution of X square, and then you'll have to define this integral X square into probability function of the G of X or X square. Therefore, to define expectation of G of X, you'll have to use G of X, expectation of this is equal to G of X into this probability must be the probability distribution of the G of X. Then only it is a valid definition. But we don't do that. We simply define expectation of G of X as sum over X, the G of X, and the probability function of the original X. That is what the statistician forgets. He forgets about the distribution of the function G of X is not used. Therefore, without consciousness, he uses the distribution of original random variable and he defines the expectation. That is why this is called law of unconscious statistician. He forgets the rule that we'll have to make use of the distribution of G of X for defining expectation of G of X. That is the original definition of expectation of, but we don't do it. But if you use this function or the original or the definition, namely the distribution of G of X, you will get the same answer. You will get the same answer, but as a rule, you will have to make use of the probability function of G of X. Yeah, similarly, if you have a continuous random variable, see here expectation of G of X is minus infinity to plus infinity G of X, but here we are making use of the probability density function of X. In fact, we'll have to make use of the probability density function of G of X. We'll have to make use of G of X and define this integral. That value is called the expectation of G, but we don't do it. We just like that have expectation of G of X equal to minus infinity to plus infinity G of X, f of X dx. That is what this law of unconscious statistician says. Okay, next slide, please. Next slide, please. Yeah, generating functions. Generating functions. You see the generating functions are, if X is a discrete random variable, the probability function P of X, then the moment generating function of x is defined as expectation of e power tx. The g of x is you hear e power tx. Therefore, the g of x is plugged in here, and we make use of again the g of x. Here also the law of unconscious statistician is used, and we define this function, and this function is called the moment generating function of x, and this function is useful to generate moments of the random variable x, like the mean, standard first moment, second moment. All these moments are obtained through this function. That is why this function is called moment generating function. And similarly for the continuous random variable, we use this definition, and through this function we can generate the moments of the continuous random variable. The only difference is here. See, here the distribution of the original random variable is used. The characteristic function can also be defined similarly. Only thing is here e power itx, the imaginary number. Here also e power itx. The difference between this characteristic function, moment generating function, is moment generating function sometimes may not exist for this x, but the characteristic function can always, the characteristic function always exists. Therefore, people use the characteristic function to prove some theorems, but this moment generating function people may not use for those random variables. The moment they exist, they make use of this function. Okay, next. Right. Oh, previous slide, please. Previous slide, madam. Previous slide. Right. See here, there are two jewels. There are two jewels in probability theory. What are the two jewels? One is central limit theorem and law of large numbers. They are really powerful concepts in probability theory, and these jewels, I listened to a lecture about 15 days back. There is an integral, and the integral, if it is a simple integral, if the function is simple integral, for example, integral some a to b x square dx, immediately you can find out the value, like integral 1 to 5 x square dx, in definite integral, you can find out the value. Suppose the integrand is very complex function. Then immediately you will not get the result. Either you will have to use numerical method or some other method by which you can get the value of the integral. But what he used was, these two theorems in probability theory, central limit theorem and strong law of large numbers, and using this central limit theorem and strong law of large numbers, he evaluated that integral, which is of very complex function, very easily. Just like that, he simulated this random variable, and through that simulation, and he obtained, he used this strong law of large numbers and the central limit theorem, and finally got the value. Of course, an approximate value. It may not be very exact value. An approximate value is immediately obtained. That is how he called it. The person who delivered the lecture called it the two jewels in probability theory. Therefore, I also put the same term here, two jewels. What these jewels say? The jewels say, central limit theorem, let x1, x2, xn be a sequence of independent random variables. This independence is very, very important. That is, it dominates the inference procedures in statistics, each with mean mu and variance sigma square. Therefore, all of them have the same mean and same variance. Then the distribution of x1, x2, xn, this is called partial sum. The partial sum, x1 plus x2 plus xn minus n mu. n mu, n times the mean divided by sigma root n. This is the square root of the variance of x1 plus 2 xn. Therefore, this is Sn minus expectation of Sn divided by square root of variance of Sn. This goes to standard normal. Normal distribution, you have standard normal distribution as n goes to infinity. As n goes to infinity. This theorem is very much used in the industrial quality control. The quality control are computed using this central limit theorem. Now, what this strong law of large numbers say? Let x1, x2, xn be a sequence of independent random variables, each with mean mu. Therefore, here also identically distributed. Then Sn, x1 plus x2 plus xn divided by n, this converges almost surely with the probability 1. As n goes to infinity, it converges to mu. Or in other words, the population, this is mu, this partial sum divided by n converges to mu as n goes to infinity. This is what these two theorems says, and these theorems are very much used in statistics. Next slide. Next slide, please. Random sampling versus population. The law of large numbers says that the sample mean, which means the partial sum, the sample mean converges to the population mean with the probability 1. Therefore, as the sample size increases, therefore, this is one of the principle needed in our sampling strategies. Namely, it is important to note that they confirm that the sample mean gets closer and closer to the population mean as the sample size increases. As the sample size increases, the sample mean tends to the population mean. This strengthens our faith that our sampling method over the census method. Therefore, many people question how your sampling procedure will be closer to your census method. Because of this law of large number principle, as the sample size becomes larger and larger, the sample mean converges closer to the population mean. That is what this strong law of large numbers says. Now, these are all, we have missed several slides in between. I wanted to differentiate between the mutually exclusiveness and the independence and several examples there. Unfortunately, we missed all these slides. Therefore, let us assume that the probability theory lecture is almost over. When the classes probably reopen for online, offline, without online, probably I will make one visit to your college and try to give a beautiful lecture for the young students, which will be useful for their study in other areas like statistical inference, all these things. Now, few suggestions I wanted to tell to our young minds. See, you people have joined now. Madam, you go to the next slide. You go to the suggestions for young minds. Now, let us go to the general lecture. Let us assume that the probability lecture is over, and I want to, as a senior person, spend a lot of time with the young students. And I want to give some few suggestions for these young minds who have joined this course with a lot of ambitions and hope. A few suggestions I want to give are there. Now I recommend these students read good books. Read good books. Good books in the sense that the books must be published by very good publishers. Very good publishers like Wiley, Academic Press. You see who publishes it. If it is a standard publisher, you buy shirts and all. You are immediately looking for some branded shirts so that it will be free from any mistakes. Like that, here also, you try to read standard books published by good publishers. Why good publishers? Because the publishers will have a team, an experts, a review team. The reviewers will be there for publishing that book. They will go through that book completely and pinpoint any mistakes entered in that book by the author. They will try to remove that. Similarly, concepts maybe wrong concepts may be there. They will advise the author to remove such concepts which are with error concepts. Therefore, try to buy good books and try to read that books that will really help you to understand lot many concepts without any mistakes. That is what I mean, read good books. Now, these books, when we were students, when we were young lecturers, the books are not very expensive. I cannot buy a book because the book will be in thousands of rupees at the time, about 20-30 years back. Thousands of rupees. Now, those books are available at a very, very cheaper price in the market as a student edition. Unlike the olden days. Therefore, buying the book is not a problem. You can buy at a cheaper price. These books will be really useful to understand a lot of concepts in statistics. See, there is a library called Anna Centenary Library in Kottayam. If you visit that library, you can see lot many books are purchased there in statistics. All of them are available for your reading. Lot of air conditioning facilities there. You can sit there and you can really enjoy reading the books there. Therefore, make it a point to visit that library after you join in the course, or if you are already in the course, kindly see that library. You will learn lot many things. And try to do some problems in the exercises of standard books. See, I was teaching in a country, African country. I used to explain the concepts and try to do the problems, the theorems and all. What they insisted was, sir, these and all we can understand from the books. You kindly throw the ideas, we will understand everything, but try to do some problems so that it will be easy for us to understand the concepts. Therefore, solving a problem in the exercises of standard books really will help you to understand the concept. Initially, it may be very difficult, but later on, you will really enjoy. You will enjoy solving the problems. That the training the students must take when you are doing a course in statistics, that really will help you. Similarly, this is a booming age, internet age. Lot of videos are available in YouTube on different topics of probability and statistics. Therefore, you spend more time listening to YouTube videos on statistics. Certainly that will help in understanding many concepts in statistics. Even now, I am spending some time. For example, in one place, they wanted to give me a lecture on hidden Markov models. Hidden Markov. Markov models we studied, but hidden Markov models is another area which is useful by the computer science people. Of course, again, statistics is used. Therefore, to understand much better, I listened to some videos which were available in the YouTube. That really helped me to understand concepts on hidden Markov models. Therefore, my simple suggestion for the young minds is that you listen to education videos on probability and statistics on YouTube. Many YouTubes are there from several universities also. Therefore, in that way, you learn out of statistics. Next slide, please. Now, what are the opportunities for statistic graduates? As your principal told, she was congratulating all of you for joining the statistics course. In fact, you are lucky, my dear students. You are lucky that you have joined the statistics course knowingly or unknowingly. You may not know earlier that statistics has this much strength, this much openings, this much opportunities. There are plenty of opportunities for statistics course. I would really say that your people are really lucky that you have joined the statistics course, and really I congratulate the college also for having started a course in statistics. In fact, the earlier teachers like Chetty, Ramchandran, Kalpanabai, Pari, all these people did a lot for starting this course in statistics course in this DRBCC college. In fact, therefore, you people, I would say, you people are really lucky that you have joined a statistics. Never discourage yourself. Statistics has a lot of strengths. It is Professor C.R. Rao told in one of the lectures. C.R. Rao, you must be knowing, he is now 101 years now. He has completed he celebrated his 101th birthday last September, and he is a pioneer in statistics. He used to say statistics is art, science and technology. Lot of opportunities are there. One slide, statistics has lot of opportunities. If you look at the TNPSC or Staff Selection Commission, there are lot many posts like you require a lot of statistics for clearing these examinations. Similarly, if you look at UPSC, you have civil services, you have IAS, IPS, Indian Forest Service, etc. You have opportunities for higher level posts. Similarly, direct employment posts are also there. Similarly, you have the banks, Reserve Bank of India and other nationalized banks, they recruit special officers. You can go to higher studies for strengthening your educational prospects like IIT, IIPS, Indian Institute of Science, etc. The last one is data scientist. This picture tells about the data scientists. See, this is a picture which was circulated by a forum which I just downloaded it. A statistics is a big elephant. The computer science is a snake, small snake. And the computer science people told, we will work together, the elephant and the snake. And slowly, the snake tells, you teach statistics, both of us will learn. You teach statistics, I will teach computer science like that. One day, the statistics is being swallowed. It is a big animal. Now this is data scientist. Data scientist. Inside there is a big animal. In a big animal, statistics. Therefore, data scientist is full of statistics. Of course, with some computer science like Python or R programming. Without statistics, data scientists cannot be successful in their career. That is what the whole picture tells about. Next slide, please. Next slide, please. Deepapriya, madam. Yeah. This is the slide, another slide, artificial intelligence and statistics. Look at the picture. Here, this picture, I couldn't see the picture. Here is, there is a mask here. The mask here, machine learning, the machine learning. Therefore, inside there is statistics, but machine learning masked it. But inside, again, statistics is there. Therefore, the statistics is playing a key role in artificial intelligence and machine learning. That is what this cartoon also says. Therefore, finally, we can say the statistic rules this virtual world now. See here, this is a book, a recent book. People talk about machine learning, artificial intelligence, like that. Here there are 4 authors. All of them are from standard universities like Stanford University, USA. They have written a beautiful book about how statistics is there in your machine learning approaches. How statistics dominates in artificial intelligence and machine learning techniques. That this is the content of this book. Next slide, madam. Next slide. Yeah, this is the book, an introduction to statistical learning, like your machine learning. This book tells about how statistics is embedded in machine learning approaches, and this is written by 4 giants. These giants are from Stanford University or University of California. Beautiful book. This can be read by a BSc Statistics graduate or MSc graduate. Such a wonderful book. This book was priced at a higher price earlier, about 4,000 rupees. Now it is available at a cheaper rate because of the wide use by the practitioners. This introduction to statistical learning. This book is available for 800 rupees or 900 rupees now. Such a wonderful collection of ideas are there in this book, which is completely useful in machine learning approaches, the statistical ideas. Therefore, that is what I wanted to say. Try to read good books. It will have a lot of information, and that will help you in your career to reach the heights. With a small introduction, probably I will wind up my lecture. It is up to you. Next slide, madam. Next slide. Any questions and clarification? Now it is up to you to raise some questions. Anything on statistics or in general also. Hello? Hello? The problem is, I don't see you, I don't hear you. Tell me. Hello? Then thank you. Thank you, one and all. Thank you for the opportunity to share my experiences and knowledge with the young minds. Thank you.
Speech. I request Mr. B. Vijay, Assistant Professor, to give
Good evening to one and all present here. Gratitude is the least attitude that takes you to your attitude. I take an immense pleasure to thank our honorable chief guest, Dr. G. Gopal, former head and professor, retired University of Madras, for his valuable presence in this inauguration, and also he explained very clear about the probabilities and career opportunities in statistics. Thank you, sir. I am very grateful to thank our management. I'm very grateful to thank our management for providing fund and support to make this occasion a grand success. My sincere thanks to our director, principal, coordinator for their constant guidance and support. I extend my gratitude to our HOD, all the faculty members and non-teaching staff for their support. Finally, I thank our students who have participated and made this occasion complete. Once again, I thank everyone. Thank you all. Live stream.
Hello, sir.
Thank you, madam.
Hello, sir. Sir, thank
Yeah,
you.
tell me.
Na
Tell-
call la varen, sir. Stream
Okay, thank you,
na
thank
call
you.
la
I
varen.
will leave now.
Thank you so much.